These are the computed problems for the unit on solids, liquids, and gases. And the first one I'm going to do from chapter 12 in Hewitt. So chapter 12, problem number 1. And it says, find the density of a 5 kilogram solid cylinder that is 10 centimeters tall and has a radius of 3 centimeters. So here we have a radius of 3 centimeters. And then here we have a height of 10 centimeters. Doesn't look like a solid cylinder, but that's what I drew. I did draw it to scale, by the way, if you check out the squares here with the 3 and the 10. Okay, in any case, we have to figure out density. And the density is, of course, mass divided by volume. And in this case, the mass is given as 5 kilograms. And we have to figure out what the volume is. And it's the volume of a cylinder, so we have to look that up. And the volume of a cylinder is the height times the cross-sectional area, so pi r squared. And this is not hard at all to look up. So now it comes out then to 10 centimeters times pi times, it was supposed to be a times, oops, I made a mistake here, that's a squared, not cubed, it's squared, times the radius squared, 3 centimeters squared. So plugging that into a calculator then would be 10 times pi times 3 squared. I come up with 283 cubic centimeters. So 283 cubic centimeters. At that point I'm going to see that the units are going to look rather strange. We like to express it in grams per cubic centimeters. So I'm just going to take the kilograms away here, and instead we'll write 5,000 grams per 283 cubic centimeters. So 5,000 divided by 283. I come up with a rounded 18 grams per cubic centimeter. Perhaps this is an alloy. I looked up a list of pure metals, and either of the common ones, gold or uranium, are relatively close. So we either got a uranium cylinder here or a gold cylinder, I guess, whatever our preference is. Chapter 12, problem 4 says a certain spring stretches 4 centimeters when a load of 10 newtons is suspended from it. So there's already some information there. 10 newtons is apparently proportional to a stretch of 4 centimeters. That means F proportional to delta x, Hooke's law. Further on it says, how much will the spring stretch if an identical spring also supports the load as shown in A and in B? Well, in A they both share the weight, these two springs, and they're supposed to be identical, so each one of them supports 5 newtons, and therefore each one of them will stretch by 2 centimeters. Part B. Each of the springs has to hold up 10 newtons, so each of them will stretch 4 centimeters each. So this one is going to be 4 centimeters, and this one here as well is 4 centimeters. This can be shown with this animation. This would be here the original problem, and the numbers are going to be different, so I'm going to let the string stretch here. The other two on the right and left will also move, but just focus on the one in the middle. Right now it starts at 203, and then it kind of goes down and it goes to 223. So this string stretches here by 20 centimeters. Now the other strings, they're identical. That means that this one here and this one here are the same string over here. So as I said in the problem, in this scenario here, it would stretch half as much, 2 centimeters in the problem. Here it should only be 10 centimeters, and watch, it goes from 203 to 213. So each of them is holding only half the load. The one on the left, these two springs are on top of each other. So with this one here stretching 20 centimeters, each of these should stretch 20 meters, so there should be a total being read of 40 centimeters. By the way, this little piece here, this connection piece, and here I made it virtually massless, very little mass compared to this one. So anyway, so this one here should stretch by 40 centimeters. And when you look at the number, indeed, that's what you can see. So each one of them stretches by 20 centimeters, which is the original amount of this one. And that's pretty much what I said in the problem that I calculated.